Good afternoon, and thanks for tuning in for our study that incorporated detection data into Razorback Sucker survival estimation. I'd first like to acknowledge my co-authors, Kevin Bestgen and Gary White. And we'd all like to thank the countless individuals who make analyses like these possible. I'm going to start with a bit of background, specifically an earlier analysis of Razorback Sucker survival we conducted. Then I'll get you oriented to the study area. Next, we'll get into some results, including comparisons to that previous analysis, and finally, some conclusions. Razorback suckers are native to the Colorado River Basin and were listed as endangered in 1991 as populations dropped to critically low levels. Several management strategies have been implemented, but the first action, taken in the Upper Colorado River Basin, where I'll focus today, was to develop a robust propagation program to buy time for the species as other strategies evolved. My co-authors and I first estimated survival rates of razorback suckers stocked into the Upper Colorado River Basin for the years 1995 through 2006. It was an annual mark recapture study using physical captures of tagged stocked fish. What we found was that capture probabilities were all quite low, which we know can affect precision of other parameters, and limited our ability to estimate some effects, such as time variation. But we did produce reliable survival estimates with important effects. Fish survived their first year in the river at lower rates than any subsequent year, and you'll see me refer to those as RY1 and post-RY1. And the season during which a fish was stocked and its total length at stocking affected those first-year rates. This is a graphic displaying all those results with survival on the y-axis and total length on the x. The things to note are the flat dashed line representing the single survival rate for any fish after its first year in the river, which was 0.75. And the total length dependent first year survival curves for fish stocked during each season. And those stocked during summer, which is represented by the lowest yellow line, survived their first year at significantly lower rates than those stocked during any other season. The mean size of fish stocked during that period was just over 250 millimeters, resulting in very low first-year survival, whatever the season of stocking. Since that time, propagation plans and protocols have evolved, and in 2015 there was another revision which incorporated some of this information and recommended fewer but larger fish with a mean size of 350 millimeters or larger, which compared to the mean size of that earlier dataset would increase predicted first-year survival by 5 times. So managers have applied what we've learned about survival of stocked razorback suckers given the tools available. Since that study concluded, stocking of these fish has continued, such that numbers are up to nearly 500,000 to date. Accordingly, there have been many more captures of these fish in sampling throughout the Upper Colorado River Basin. Plus, there's been increased deployment of passive detection technologies throughout the Upper Colorado River Basin and the San Juan River Basin just downstream. That technology includes permanent cross-channel antenna arrays, portable flat plates and wagon wheels, and submersible ultrasonic receivers, and has resulted in over 700,000 records of razorback sucker detections. Of course, this has led to an interest in what all this additional data, particularly detections, can add to what we already understand of this species' survival. So the purpose of this study was to provide updated, precise parameter estimates for razorback suckers stocked into the Upper Colorado River Basin. And we set out to do that by adding physical capture data both through time and space and by incorporating detection data. Our study area includes the Upper Colorado River Basin, which drains portions of Wyoming, Colorado, and Utah, and includes the Green and Colorado River subbasins. We defined 5 reaches, which have been used in past studies, and in our case denote where razorback suckers have been stocked, shown generally by the yellow stars. Physical captures of those stocked fish came from sampling for various projects within those reaches as well as upstream, downstream, and in between. Detections of those stocked fish came from the many antennas throughout the Upper Colorado River Basin. We always have to keep in mind when and where these antennas have been deployed as we interpret the data that they're supplying, and we'll see that when we get to results. So we've got much of the upper basin covered for both captures and detections of stocked fish. But we know that these fish move between the Upper Colorado and San Juan River basins. So in this study, we also included captures and detections of upper Colorado River Basin stocked fish that occurred in the Colorado and San Juan River arms of Lake Powell and in the San Juan itself. We analyzed the data in program MARC using the Barker data type, which estimates survival, capture probability, and resight or detection probability, as well as several other parameters I won't get into today. Our final dataset consisted of over 331,000 Razorback suckers stocked into the upper basin, 93% of which were never seen again. The remaining 7% were encountered from 1 to 6 times, with the vast majority only encountered once. And I'll break these numbers down even further in just a bit. So let's get into results, starting with a list of effects in our top model. Survival was a function of year and included the effect that first-year survival could be different from subsequent year, and those first-year survival rates were affected by a fish's total length at stocking and season of stocking. Similarly, capture probabilities also varied by year, with first year and subsequent years differing, and first-year capture probabilities were a function of total length at stocking and the reach where fish were stocked. Resight probabilities were a function of year and the reach where fish were stocked. I'm going to look first at capture probabilities, which we know strongly influence other parameters. To save time, I'm not going to get into all the details of the many effects I just mentioned for the capture probability parameter. It suffices to say that capture probabilities were low. For 350 millimeter stocked fish, which is the current minimum mean size, first year mean capture probabilities for the entire study was 0.06, and even lower after the first year. We know that low capture probability has always been a problem for this species, hence the interest in using detection data to aid estimation, which we'll look at next. So we have detection or resight probabilities on the y-axis and year on the x, and we only started this graph in 2012 because estimates prior to that were essentially zero. Resight probabilities for fish stocked into the Green River subbasin, the top 2 green lines, were greater than those for fish stocked into the Colorado River subbasin, which are the bottom 3 purple lines. Now recall my caution to bear in mind when and where these antennas were deployed as we look at the patterns here. Overall, detection data provided the most information about the Green River subbasin. Razorback suckers stocked into that subbasin accounted for 60% of all stocked fish, while 87% of detections came from antennas in the Green River subbasin, and 90% of detections were of fish stocked into the Green River subbasin, which explains the higher resight probabilities for those Razorback suckers. Now let's look at the estimates through time as they relate to antenna use in the Green River. In 2012, we have our first useful estimates, and that's when portable antennas were first deployed seasonally at a known spawning area. Then in 2013, we've got an increase in resight probabilities when greater effort was established at the spawning bar and a fixed array was installed in a diversion canal suspected of entrainment. Then in 2016, we've got our next bump up, and that's when another fixed array was installed in multiple locations across the main channel adjacent to that canal in the Green River. In the Colorado River subbasin, there are 3 fixed arrays, but they aren't ideally located to detect the most Razorback suckers, and low or non-existent flows preclude year-round access by fish. Also, less was known about Razorback sucker spawning locations in that subbasin, making strategic deployment of antennas less straightforward, though that's been changing in recent years. Now I want to return to that number I mentioned earlier, that only 7% of stocked fish were ever encountered throughout the study. Of those ever encountered, 62% were only physically captured over those 15 years, while 30% were only detected, and that was just in the last 5 study years. In other words, we have nearly half as many detections as physical captures in only 1/3 of the time, which illustrates the abundance of data we might expect from this technology going forward. Now, since capture probabilities and resight probabilities are really here to help us estimate survival, let's get to those results. I'm going to start with survival of fish after their first year in the river, which are independent of stocking variables. Here we're looking at subsequent year survival on the y-axis and study year on the x. There's quite a bit of variation over the years, but generally increasing estimates through time. These values average out to be 0.80, and we're quite precise with coefficients of variation mostly in the single digits. In our past analysis, we estimated a single subsequent year survival of 0.75 with a low CV. These might look comparable, but really we're looking at apples to oranges because there was little overlap of years between studies and we added time variation in this study. So for fun, I ran this data set using as similar a model as possible to the one in that previous analysis with no time variation, and produced a point estimate of 0.87 with a tiny CV, which makes sense because all of our data went into this one estimate. So now maybe we're comparing apples to pears, but that model and any other without time variation were ranked very low. Nevertheless, the relatively high and precise estimates from our current top model should be pleasing to see. Now let's move on to those first year estimates that also varied through time and were a function of total length and season of stocking. This is just a general look at the pattern of results for an unspecified year. We've got survival on the y-axis and total length curves for Razorback Suckers stocked during each season. We're seeing again that bigger fish still equals better survival, and fish stocked during summer months, which is the lowest yellow line, have significantly lower first-year survival than fish stocked in other seasons. And that all supports what we've seen previously. If we wanted to see how those vary by study year, we'd have to look at 15 of these graphs. Instead, I'll just take those 350 millimeter fish and demonstrate how the rates vary for that sized fish among years. So this is first year survival of 350 millimeter fish stocked in each year. I've added 95% confidence intervals, so you can see that survival of summer stocked fish was significantly lower, and that holds true for all sizes of fish. If we want to compare these rates to our previous work that only had point estimates, we can look at the mean values for each season. So a 350 millimeter fish survived its first year in the river at a rate of 0.57, 0.46, or 0.18 on average, depending on the season it was stocked. The point estimates from our previous work are on the far right. They were lower and less precise. But again, to be more comparable, I generated seasonal point estimates from a similar model in this study without time variation. Those are shown here in the middle column. And the estimates are similar to the previous analysis, but much more precise. While that's interesting, we remind you that those are from a low-ranked model and recommend that rather than continue to compare these apples to pears, we just commit to the oranges and move forward with the most precise estimates from our most recent data set and the variables that influence them. That was just a brief look at our results. In our report, which is under review and available soon, we dig deeper into possible explanations of those results. For example, we saw that summer stocking resulted in low survival, so we also looked into the relative influence of those summer stocked fish in every year. By overlaying the percent of Razorback Suckers stocked in the summer, which is the dashed line, on top of first year survival for each year, the solid line. There's certainly no correlation here, but if we look at the years with the lowest and highest survival, 2006 and 2014, we see that those years had the highest and lowest percent of summer stocked fish respectively. Certainly that's not the only factor influencing annual variation in survival, it's just one of the factors we're exploring more. In conclusion, we found that incorporating detections alongside traditional physical mark recapture data produced higher and more precise survival rates than we've obtained in the past. We also found, as in our 95 to 2006 analysis and a couple of others in between, that season and total length continue to be important influences on first year survival. So those should still be considered when management decisions are made. And finally, the temporal and spatial distribution of detection technology strongly influence resight probabilities, and therefore survival estimates, of fish stocked into various reaches, and should be carefully considered for any future deployments. Thanks for your time, and if you have any questions, you can contact me at the email at the top.